Hello, everybody. Nice to see so many people are actually here, interested in IPv6. The last talk I was giving was 6 weeks ago. The room was not very full, put it like that. So, nice to see that things can be different here. Okay, I'm doing a talk about IPv6 insecurities. Who am I? My name is Mark, or vanHauser. Being around for 17, 18 years in IT security, DHCP, hopefully you know the hacker's choice, which is, fun fact, 2 months older than the IPv6 protocol. Yeah, basically I'm a Unix guy, network guy, but yeah, if you're long around, you see everything. Who has already heard the previous talk I did here at the Congress or at another conference? Can you please raise your hand? Whoa, it should be around 10, 12, pretty good. So you will hear new stuff, don't worry. It won't be the same. Who played with IPv6 already? Wow. I would say there's maybe 40, 50%. That's pretty good. And who has either IPv6 at home or at the office university? And please keep these hands up, because that was way more than I expected. So maybe you should read on Heise Newstacker that IPv6 is available already everywhere. Pretty cool. Really, more than I expected. So, because normally what we see is like that, IPv6 somewhere in a distant, bright future, which we of course know will never happen, we will have maybe IPv6 if we can't avoid it at all. So this is what usually people think about IPv6. Same what people think about IPsec or DNSsec, whatever, is something which will never happen. Well, the reality is, we already have the future here. We have IPv6 already in all the operating systems, activated. So it's already there. All the routers, since a few years already, IPv6 comes included, but has to be activated. But in the end operating systems, it's all there already. So, let's start a little bit with the basics and some final question. Who knows already about IPv6? Yeah, that's same as how many have played with that. It's okay, so I can't skip that. Because I heard I only have 45 minutes. I thought I would have 60 minutes, so let's see how I can handle that. So, let's start with the basic. IPv4, we have 4 octets, an IP address which looks like that, and we have 4 billion numbers of addresses. Looks good so far. IPv6, we have 16 octets, or 128 bits, for those counting in bits, which gives us a very large number of addresses, which is so much, I don't know how to express that number, but let's say enough. For a while, but yeah, for the next decade maybe. But this is how an IPv6 address looks like. So you see you have some letters in there, so you see it's not only numbers. So how is this done? 2 octets, so 2 bytes, are presented in hexadecimal, separated by a colon. If there are leading zeros, they can be omitted, so that would be 0004, but you can just write a 4 then. And the longest chain of zeros can be replaced with 2 colons. This is a way to make a long IPv6 address shorter, if it's possible, from the address. A typical subnet, and this is the standard subnet which should be used everywhere, so it's not, some people will maybe use it, this is what everybody will use, is a /64. /64 for just a subnet means it's 4 billion times the whole internet. That's just a subnet. That's pretty much, actually. There are reasons for that, which we don't have time to get into that, but that's how large it is. Another thing which is special here, there are no broadcasts, but there are multicasts. Multicasts in IPv6 are only local. So only on your local subnet, on your local site, on your local organization, there you have multicast. You can't access multicasts from remote. That's not possible. We have lots of features. We have auto-configuration, which is, in my opinion, the coolest feature in IPv6, which means you can plug any machine anywhere, and it works out of the box. Same like in IPv4 DHCP, but you don't need DHCP anymore. Not necessary. IPsec is mandatory, so it must be there in every device. You have mobility, which is would nice to have feature. So I'm here with my laptop, have active sessions, and I go on a train, I keep the same sessions open, I'll fly across to Vancouver, and I keep my sessions open because I'm mobile with my IP address. Also a nice feature. And of course, enough addresses. And not just theoretically. This is how the IPv6 header looks like. If you know IPv4, you know there's lots more stuff. Yeah, so this looks very clean. So where are the differences? What is the difference here to an IPv4 header? Well, the version, of course, is different, yes. What's also very nice, I mean, IPv6 is 15 years old. What they did, they're keeping the stuff part of the stuff here, but they rename it to make things simpler. So if you know IPv4, it's not the same names, the terms you're using, just to make things simpler for you. So what is the difference? There is no header length, which you have on IPv4, just because the header is fixed. It has a fixed size, so we don't need that anymore. It's 40 bytes. It has no identification field because they said, oh, in IPv4 we thought it could be necessary, we thought it's not useful, so we drop it. There is no checksum. Checksum is all done on the upper layers. There is no fragmentation field. So, interesting question, how can a packet be fragmented if there is no fragmentation field? Is fragmentation not possible anymore? Of course it is, I'll show you in the next slide. And there are no options anymore. I don't know if you know IP source routing and stuff, and other options there are. These are not in here. So how does this work? Every option, and this includes fragmentation, is an extension header. This is fragmentation, this is source routing, we still have that because IPv6 is very secure. IPsec, destination options, and some other stuff. That's all in extensions. And this is how it looks like. You have an IPv6 header. You can have as next header a routing header, which is source routing. You have the fragmentation header, you have the UDP header, and then you have data. And these are extension headers. They are extensions because they're only there if they are needed. So you only have the fragmentation header if the packet is fragmented, which is useful. But you already see, okay, we have headers. Okay, which headers are they? Can a header come twice or 3 times? What is the order in which the headers may come? Must there be this first and the other one after? What is if the other way around? You see already there's lots of complexity here, which creeps in because you're doing that. So in theory, IPv6 is much simpler than IPv4 because fixed packet size and what is in there, pretty simple, everything is extension. Sounds simple. In theory, yeah. That would be 10 minutes, but as I have 15 minutes less time than expected, let's put it like that. IPv6 was designed 15 years ago with the security models from 15 years ago, which means the trust model is basically everything which is local is okay. Yeah? There is no enemy local. Everything else where they say, oh, IPsec. Use IPsec, everything is fine. But of course, deploying IPsec is a pain in the ass. So I'm not sure we'll see it anywhere else than in some military whatsoever nobody wants to know. Then people were not, well, they were technicians, but not necessarily clever. They said auto-configuration. Auto-configuration is cool, just plug and play, no need of extra software like DHCP client. Who needs that? So if you have auto-configuration, everything's cool. Yeah, then they forgot something. What about the DNS server? Oh. Do we need a DNS server? I mean, people can type in the IPv6 addresses, right? So who needs the... Okay, now we have to find another solution. Well, they could use DHCP for that. Yeah, and that, of course, beats the purpose of auto-configuration. So what happens then? People write RFC to solve the problem. And there are, of course, two different solutions. Which one are implemented depends on the vendor, because there's no RFC which says this is the right RFCs to implement. So every vendor is implementing different features for IPv6. And this is the main problem. There is no standard, this is IPv6 standard and has to be implemented. There's nothing like that. Everybody can implement what they want and say IPv6 and support it and everything's fine. So, IPv6 vulnerabilities. So this is by year how many IPv6 vulnerabilities were found. As you can see, IPv6 is a very simple protocol, so what could probably go wrong? Come on. The earliest numbers I have are from 2002. So we see, okay, we get a level of about 15 per year on average. 14 per year, sorry. This is what I expect it will be for 2010. Because when you get assigned a CVE number, it's not necessarily published in 2010, because communicating vendors until you can publish it can take 6 months to 12 months until the CVE is published. So even if it's December next year, there will be CVE numbers being published with for 2010. So this is, from the statistics, what I expect will still come. And this does not include my CVE entries. Currently I have 5. So, kids, in 2005, I did the first talk on IPv6. It was the first talk ever on IPv6 security from a hacker side. Of course, Cisco made lots of nice technical presentation on how their products are very nice. But that was actually everything there was until that point. I introduced the IPv6 attack toolkit and demonstrated some of the fundamental weaknesses. So not something very sophisticated or special, just the fundamental stuff. Like ARP spoofing you have in IPv4, you have the same in IPv6 because protocol security 15 years ago. It's just called neighbor discovery spoofing. And it's basically the same. Instead of sending an ARP request, you send a neighbor solicitation. And the target system sends a neighbor advertisement. And you can do the same thing as you can do with ARP. You can spoof that. So there was a tool which sends neighbor advertisements for every neighbor solicitation which is sent and say, this is my IP address. Yeah, this is also my IP address, and this is my IP address as well, and get all the traffic to you. Then we had duplicate address detection, denial of service. Same as IPv4. A system sends neighbor solicitation for the IP address it wants to use itself. And if there's no answer, nobody else is using this IP address. Wonderful. So of course, I wrote a tool which would say for every solicitation, I'm using this IP address, yes, I'm also using this IP address, and the systems would not be able to participate in the IPv6 network. Then, man in the middle with redirects, something which also works on IPv4. Also, there's no public tool for that available, but here's one publicly available for IPv6. Let me skip how this really works. It means that on the local network, you can transfer all the traffic to you, so the victim thinks you are the router for whatever target. Where you have DHCP, you have auto-configuration. So on IPv4, you could run your own rogue DHCP server. In IPv6, you would be sending router advertisements. So you have a tool which tells you I'm a router and I'm a high priority router, so you have a higher priority than the real router and stuff, and then get all the traffic. So this was the stuff I had in my talk 5 years ago. So now comes the new stuff. There is an easy way how you can kick the default router, and by that remove any router availability on the local network. And you just send your own router advertisement if you want to, but spoof the router advertisement of the default router with a 0 lifetime. What happens? The systems will receive the thing, 0 lifetime. Okay, the router is announcing it's not there anymore. This is what a router sends if it's shut down. Tells them, here, I'm a router and I'm not available anymore. So delete me, please. You spoof that packet, boom, route gone. Okay. You can resend your own router advertisement just to be sure that you're sure you get all the traffic because you are then the default router. But you can also omit that, not send your own default router. Yeah, how you can spoof it so that this router doesn't see that is another topic. We're getting back to that. But if you kill all routers, so you're not sending your own router advertisement, the clients will think everything is local. That's what is defined as a standard. If a system has IPv6 connectivity, but knows of no router whatsoever, it assumes everything is local. The whole global IPv6 internet is local. Yeah. Okay, works for me. More stuff. Send a router advertisement and systems become dual stack. So if there's no router advertisement or you don't activate manually, so this is my IPv6 address, the system thinks I only have IPv4 and only uses IPv4. If you don't have Teredo or whatsoever there. But once there's a router advertisement, all systems which are in default configuration become dual stack. You can port scan on IPv6. And if you don't have the Windows firewall, but you use, for example, whatever commercial one, some of the commercial ones don't filter IPv6, but just allow it through. So, full port access, so full port scanning on the local network, just by sending one router advertisement. They will prefer IPv6. Yeah? So if you use a tunnel, so you announce yourself as a router, you say IPv6 on the network, they will start using IPv6, you tunnel to the real internet, and you have a man-in-the-middle attack. Especially interesting if you're announcing remote network addresses local, let's say for PayPal or whatsoever, yeah, and now that network prefix, and every system thinks, oh, this is a local system. So you see how much stuff you can do there. Unbelievable. Router advertisement flooding. I wrote the tool to see what happens if I just send 1 million router advertisements coming from seemingly different routers. What could possibly happen? I mean, that's such an obvious attack, sending random router advertisements, nothing should really happen. That's what I expected. Except if you're a Cisco or a Microsoft, then this might come to you as a surprise. So what happens if you have a Cisco firewall or any iOS or any Windows system, 2008, 7 or Vista, or 2003 or XP if you enable IPv6, denial of service. 100% CPU, no activity possible anymore. Just by sending some router advertisement flooding the network. And some old Linux, but of course fixed long ago. Come on. Cisco just fixed that. Yeah, so these are the fixed numbers for iOS, for ASA. They should be out already, but I don't know the numbers at the moment. Microsoft wrote me a very nice letter and said, yeah, interesting, but this is a design issue. Sorry, we don't deal with design issues. So I know this is the emergency response team, and of course, they have no power. They can only tell people, please do, and then some other management say, no, sorry. Maybe in some service packs, but that's what I got about some private channels back, maybe in some service pack, maybe, because doing something like no more than 100 router advertisement in routing table, this is kind of too hard to do, maybe. So they told me, please put some more pressure on the topic and then maybe this will get fixed. So, and by the way, even Apple got this right. This is a command, this is part of the IPv6 tool package. This is the command line which you should not use. Because every Windows system, firewalled or not, doesn't matter. Doesn't matter if you have Microsoft firewall or like me, I have a semantic firewall. Doesn't matter, it's no protection. Yeah, denial of service, nothing possible. So don't do this here on the local networks. Yeah, please. We are nice people. We're just pointing the fingers. Yeah? Someone else is pushing the button, maybe. Okay, a completely different topic. So please understand, I can only talk about 60–70% of the stuff I found, I researched and stuff, because it's just too much. I wanted to get at least a little bit of a red line through my talk, which is agreed, very difficult. I don't know if you see one. Maybe there is none, but remote alive scans, which means what are systems available on a remote network, will not be possible to do ping scans because the address space is just too large. Remember, /64, 4 billion times the whole internet. So it's not possible to do remote ping scans. Some jerk said that, actually it was me 5 years ago, if those few people remember. But then this year I thought about, is this actually true? And I started to do some statistical research. How do we identify remote systems? We can't scan the whole range, obviously. Yeah? If we would do that, if we say we have more than 1 million time gigabit Ethernet connection, and we can send such a big amount of packets, and the people can actually respond to that, and the router infrastructure is supporting it, blah, 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 would still take something like 50, 100 years. That's, of course, not feasible. We don't have broadcast, so not something like ping, remote broadcast address, and some systems will answer. We don't have that either. We have search engine in databases, so we can Google for IPv6 addresses maybe. We have DNS, where we can explicitly ask for IPv6 addresses like www.google.com. Give me the IPv6 address. There's none, because it has a special IP address, but this is how it would work. And you have common addresses. And I'm combining these two to get a pretty good view on what is really there. Of course, there are lots of black spots in my approach, because what I will show you what I did, I ran through all the DNS entries, I scanned through all the networks, so I really created lots of packets on the network. But I'm, of course, missing stuff. For example, like DSL connections. Asia has lots of IPv6 DSL connections. These are not in this statistical analysis. Other stuff, like routers in between. There is stuff I could do there, but that was not my focus. My focus was more on server side. So this is what this statistic is more oriented to. So, search engines. I dumped various IPv6 directories, and there are quite a few from them. So I got 17,000 possible domains and subdomains identified, just dumping all the database search engine stuff. Then I did some DNS enumeration. For all the 17,000 domains, I brute forced over 3,000 host names. Found lots of systems, and from these systems, I looked how many unique IPv6 addresses come up. That was something like 15,000. In 7,000 networks, and for that point, forget that. 7,000 networks, which are actually not that many, if you think about that. But not a problem, we come to that. Now, unique host addresses. This is the host part. So if you have an IPv4 address, you have 192.1.1. That would be in a C class, the network part, and the last .1 or .100 would be the host part, the local host part IP address. And here there would be 5,800 unique host addresses. I said, okay, what can I do there maybe? I made a statistic of all the unique host addresses, how often they will come up. And you see, there is some spike until here, and then it's not very steep. I thought, okay, if I scan all the networks just for the 300, 400 most common addresses, I will find many more systems. Okay, so I did a host address analysis. How are these IP addresses that I found? How can I group them? So first I saw, okay, some are auto-configuration. Some are configured by hand. Some are DHCP or hand. That's sometimes hard to distinguish. What does that mean? Auto-configuration means is this either done by the MAC address? So if, let's say, some company has only one vendor there, most of the MAC address is the same, very easy to scan. Privacy option means will be random and will be regenerated once a week, for example, depends on the configuration, so not very useful for us. And something like totally random fixed stuff. Yeah, by hand, it's either clear pattern or it was random. And DHCP even on IPv6, which is one of the issues, in my opinion, is it hands out the IP address sequential. So if you know the starting point, very easy to enumerate the rest. If you got one, you got all, and it's easy to find. So here, with a MAC address, you have a 24-bit key space per vendor ID, more or less, some or more, it depends on the vendor ID type. This is scannable. Yeah, privacy option fixed random, of course, this is bad luck. By hand, if it's a pattern, easy. If you see the pattern, done. If the random, of course, doesn't work. And we have DHCP. If you find an address in a DHCP address space, piece of cake. So, and auto-configuration, if they use the MAC address for that, it's also kind of easy. By hand, what are people using there? So this is just the obvious stuff. There are some more, but I wanted to keep the slide somehow simple. Yeah, you have something like 1, 2, 3, or very common is service port, like 80 for the web port, for the web server, 53 for the DNS server, or if they have more DNS servers, this would be 1:53, 2:53, and so on. Or the other way around, first the service port, then counting upwards. Some use even the real IPv4 address, which is okay. And of course, people who like to make some fun with boop babe, dead beef, whatsoever. But these are less common. Then you have the DHCP address space. Actually, this and this is what is in the literature. So this is what you usually find, because people do what's in the literature. Even passwords. I mean, how often you see Cisco as a password on a Cisco router? Because it's in the example configuration and documentation and stuff. Works. So also, this is not a very large key space. So all in all, this is auto-configuration, this is the hard DHCP or hand stuff, which are very hard to identify, random privacy stuff, IPv4 addresses. And this is the easy DHCP, easy hand-configured stuff. Yeah? And this is what we can very easily find, but just using basic, regular patterns. How many? Could it be millions? Of course, way less. So I did a live scan on all the found networks. Brute force 3,000 host addresses, the 3,000 host addresses based on this address space. And I found, wow, 380,000 systems alive. That's way more. And so on and so on. How do I find more networks if I can't just scan these networks? How can this be? Because there are lots of routers in between. You say, oh, sorry, this system is not available. And then you have some more networks identified. This is how this works. So this is why more networks are in the output than in the input. Weird, but, well, that's how life is, or IPv6. So, but from the over 3,000 host addresses I tried, only 2,007 were really active. So, and if we look at this graph, oh, this makes sense. So, at this point, this is what we actually have to scan for, because this is what people are actually using. So, to do an effective scan, we just have to scan for about 2,000 IPv6 host addresses, and that's it. And then we will already have, depending on the configuration, between, on average, 70–80% of the whole IPv6 addresses in a destination network. And this is something you can do in just in a few seconds. I did some reverse DNS entry analysis to see what are the DNS host names people are supplying, to see is this different to IPv4 and what are they using, what are the most common ones, what are the least common ones, so to have an effective word list for that. Did this as well, and here again you see we just need about 1,000, 1,200, 800, somewhere wherever you want to put that. These are the active host names people are using. And actually, how you work your way is like that. You do a DNS brute force on stuff you found alive. You get new DNS entries. You put these new DNS entries in the alive scan. You get new alives. The alives you put back in the DNS brute forcing, and so on, until you found all the systems. This is the basic algorithm I did with my research, and how you would do a remote penetration testing. And alone by DNS brute forcing, you will get maybe 90% of the systems, but but by systems here I mean servers. Not necessarily routers, because they have very weird names, but at least of the servers. And you just need 1,900 words to get that. With the light brute forcing, I found you get about 66% of the systems with just scanning for 2,000 addresses. And this you can scan in 1 to 20 seconds. And if you combine the two, you get above on average, because on some networks you will find 0%, because everything is random and maybe nothing in the DNS or whatsoever, and the others have everything in DNS or everything is easy host addresses. Yeah? But on average you will have 90 to 95% of servers by just a few seconds. So much about my claim 5 years ago, you can't do remote host scanning on IPv6. But I'm not done here. We have more stuff. Taking over the multicast listener. Multicast is very, very important in IPv6. If you want to talk to routers, to the NTP server, to an S server, every service has their own multicast address and listens to that address. So you can send a packet, let's say to NTP servers, and all NTP servers, they get that multicast packet. So this is essential for IPv6 to work. And I was thinking about, okay, how could this go wrong? Let's take a look at the protocol. So this is how it works. There are routers on the network, and one router, and I will tell you later why this router is selected, sends periodically multi-listener discovery general query messages on a network. This means who wants to have multicast listener packets? Who on the network? And let's say this is a DNS server, system A, and it reports, I'm a multicast DNS server, and I want to have DNS traffic, DNS multicast traffic, please send it to me. And it sends it to all routers on the network, which is, again, its own multicast address. This router then receives this packet, and by different routing protocol like PIM or others, they send it to other routers so they know, okay, if there is DNS multicast traffic, I have to send it to this router so he can pass it on to his network. So this is how it works. So I was thinking, how can I prevent that? So I thought about, okay, let's spoof MLD, multi-listener discovery done message. That would be sending as A, telling, I don't want to receive DNS multicast traffic anymore. But what happens is that the router, if he sees, okay, he's telling me he doesn't want to receive the traffic anymore, there might be somebody else still wanting that traffic. So the router sends again a packet saying, really? Doesn't really anyone on the network want that kind of multicast traffic anymore? And then, of course, system A replies with, I'm still multicast and I want that traffic. So that was not working. Well, I was thinking, okay, what else can I do? Yeah, I was very sad. So first we want to become the multi-listener discovery query router. So this one. So that this is not the sending router, but I'm the sending router. This is the first I want it to be. And this is basically very, very easy, because this is the source code. This is the source code how this is selected. If router is smaller than router 2, then the new master is router 1. Smaller means the link local address. The link local address is FE80, and then normally the host part is the MAC address. But you can configure it. And the lowest one is FE80 and all zeros. And I've never seen that anywhere configured. Even Strato, who already do pretty good IPv6 stuff, they do FE80 and then finally a 1. Yeah? But still, I can win that. Didn't try it there, of course. But just basically it would work, of course. So this is how it works. So first, I spoof a general query message as FE80 and everything 0. The router sees that and then says, okay, I'm not the general query router anymore. Yeah? This is this router here. So it doesn't send it anymore. Okay. So if I now spoof my multi-listener done message coming from A, we still have a problem. We must send the general query message in a special interval, let's say like every minute. If we don't do that, the router assumes this router is dead and starts sending that again. So we can denial of service a few packets, but we need to send that packet. We need to send this general query message, which goes to every system. Otherwise, the router says, the router is not there, I have to send it. So what we have to do, we have to spoof a query message with the multicast or router MAC address so that the router gets the packet, but the client doesn't. And this is only possible because IPv6 has special MAC addresses for multicast addresses, which has another very nice feature I'll show you in the next vulnerability I found. So how we do the attack is we spoof the general query message at FE80. So this router is out, it's just passively listening on everything. We spoof the done message coming from A, and then we send the general query message only with that special MAC address, which only this router accepts. But this one will say, oh, this is not a MAC address for my destination, so I'm not taking the packet. This way, he still thinks, oh, the router is active in sending, and that's it. That's how we can deny all the multicast traffic to the network. Hopefully that was not too in-depth, or I'm not too bad in explaining, but actually, we did it. Let's keep it at that. Another nice vulnerability I found, and especially when I researched that part, anybody sniffing. Actually, kids, in 1997, I found a vulnerability on Linux where I could see on the local network if a Linux system was sniffing or not. Yeah? Sending a packet, if it was sniffing, I would get a reply. If it was not sniffing, I would get no reply. And in IPv6, we have the same again, just with IPv6. And this is how it works. We send a ping to the target with an unused multicast MAC address. So what happens if the system is sniffing? It will ignore the multicast MAC address and send a reply. If it's not sniffing, it will see that the multicast MAC address is not fitting to the stuff I'm looking for, so I'm ignoring the packet. And that's basically it. Yeah? Vulnerable Windows and Linux. On any Windows, any Linux system, you can see if it's sniffing locally on the network or not. And it doesn't need to sniff just on IPv4 or on IPv6. So even here, even whatever they do, you can do that. You don't have to use ping for that. You can do neighbor solicitation and get through any local firewall they are running. Doesn't matter. Yeah? By this technique, you find on any local system if it's sniffing or not. Dualstack, IPv6 only, whatsoever, it doesn't matter. And to show you how easy it is to do IPv6 stuff, finding this vulnerability and this vulnerability, how much time did the whole stuff take me? What do you think? Who thinks it would take a week? Yeah? When I'm on the beach most of the time, yes. No, actually it was 2 hours. Inclusive writing the code, reading the RFC, finding the problem, testing. That's how easy it is. Our IPv6 is such a low-hanging fruit. You don't have to grab like this. It's just like, oh. So, side channels, I looked just very shortly. I just once had an idea, so what is their side channel? Because it was a big topic in TCP and IPv4. What are side channels in the protocols? And then just after looking 2 minutes at everything, everything is a side, you can use as a side channel there because there's just too much functionality. And I could rant some more about how firewalls are using IPv6 and what they try to filter and what to. You can get anything through any firewall for side channel stuff, yeah? Because they don't filter really the traffic because they can't. Would be another topic of a talk. So, but all in all, don't be scared. Yeah. IPv6 is really highly complex. In the beginning, it looks very easy, but the more you look into it, and even for me, I did lots of stuff in IPv6, it really balls your brain. Yeah, it's really highly complex stuff. It's an intellectual challenge. And if you're tired of finding the 100th cross-site scripting in some guestbook PHP application nobody uses, and you want to do some more interesting stuff, you can do some more IPv6 stuff. It's really low-hanging. If you're not that good, and hacking doesn't matter. As I showed you, 2 hours are enough, and you can do a whole talk just about that and spare the 75 euros for the next ticket for the next Congress. 2 hours, come on, that's easy. Which is one reason why I'm not releasing the whole DHCP IPv6 toolkit. There is a new update out there, and if the DHC server would not be down at the moment because the ISP has problem with the machine, so hardware problem, I'll come to that. Let's get on. I'll come back to that, sorry. How to get IPv6 to your home? I will leave that in the slides. This is how you can configure IPv6 to have it in your home network, so you can play around with that. Creating an account, request a tunnel, so some organization stuff, no technical configuration necessary. Then either you configure a static tunnel in Linux. This is how you do it with a special software, which is also available for Windows. Install a software, configure something in the conf file, start it. I think everybody can do that. Let's agree on that. And then this is how stuff you can do on your local network, so every system can communicate over IPv6, and this is all you have to do. It's not much, and then you have IPv6 in your home network. And if you have a Fritz box, for all the current models, there's a new system firmware upgrade, and then you have IPv6 624 enabled. So you just have to click on the Internet tab, click on IPv6, click on Enable, and that's it. Really, really easy. What is new in IPv6 in my package? DNS brute forcer, more payloads for the fake router, really very fast traceroute. It just needs 1 or 2 seconds for the whole traceroute process. A fuzzer, flooding tools, and so on and so on and so on. The live stuff, so the remote live scanning stuff, I'm still fine-tuning that. And because this can be misused, this is one of the several tools I'm not handing out at the moment. Only for those people who are actively contributing. Because the more people contributing means the more people researching IPv6, the more issues being found, the issues being fixed, the more secure we will have an IPv6 network. But don't worry, over the year I will publish everything. And there we will have DHCP client spoofer, DHCP server spoofer, DNS6 spoofer, and so on and so on and so on. So, if you want to have the full package, send in patches and new tools. And you will get everything, even get full subversion access to the repository. I do a complete public release somewhere in 2011. For everybody else, this is the new public version. As I said, the server is currently sadly down because the hardware has issues. No clue when it will be fixed, as usual. We have different life, we do other stuff than just maintaining some web server. You can download it here. Lots of new tools, multicast listener, spoofing tools, DNS brute force update, and so on and so on. Lots of new stuff. More than enough to play with. Somewhere in January, I will start a space where everybody can contribute on how do I configure my Linux system so it's secure on IPv6. How do I configure my Cisco ASA firewall or whatsoever. We'll put that into some public wiki, which will be under that address. Everybody, of course, can add to that. And if you have any questions whatsoever, and the question is not, can you please send me the full toolkit, because you saw the rules, please email me, ask me anything. I usually actually answer until it's totally nonsense. But otherwise, I usually answer. That's it. I get the sign.
You don't have another 5 minutes.
Oh, here it says time is already up. Okay, thanks. Have fun exploring IPv6. I'm here. I'm here if you have more questions, and I think for those not running away, they can actually ask questions.
Yes.
Hello. Do you have any ideas on how to mitigate the problem? Like we have this rogue HP printer that claims to have a route to the internet, and it just sucks in our network because nothing works.
Yeah, that's actually lots of issues. For example, also if you have a Windows box and click on share my IP connection, the Windows box thinks I'm in a router now and also start sending router advertisement, by that doing a big problem. Though the best thing you can do is disable auto configuration, but of course this is not what you want to do.
Yeah.
So what this needs is vendor updates.
And any
Kick
plans
their
when
support
they are available,
lines.
or no?
One more question over. Okay.
Yeah, so there's a question from the peace missions. So it was at the beginning of your slides. The one asked, hi, just looked at the slides for recent advances in IPv6 insecurities. Many threats are mentioned, but I don't see any countermeasurements, maybe Savvy or anything. And he posted a link against source address spoofing.
The question is, what are the countermeasures against all the stuff I was telling? There are actually two or three countermeasures. First is IPsec, of course, obviously. But deploying IPsec, pain in the ass. There is SEND, Secure Encrypted Neighbor Discovery Protocol, which I would make another talk about the issues there once it's deployed. Why that's a problem too. But it's too early. And it's not supported anywhere so far. And the third options you have is secure client configuration. But that's an issue because you can't disable all the stuff you want. And it depends on the Linux version, on the kernel version, on the operating system. So it's, at the moment, not much you can do. The girl over here had a question. Why do the others can get you a question as well?
So you do a DHCP request and get an IP, and then you enumerate upward and downward. Can't you get all the IPs from that for your scan?
I don't get your question, sorry. Again,
Okay.
kannst du auf Deutsch sagen und ich
if you
übersetze.
do a DHCP request and you get an IP back, can
Yes.
you just enumerate up and downward from there
Yes.
to get all the IPs?
Yes.
Then why did you do all that statistical analysis to figure out the IPs?
Because not everybody is using DHCP, especially in a server environment. Yeah? But some do. And some configure by hand, some do just use the MAC address, so normal standard auto configuration feature. I wanted to see what is really useful to use. Yeah? And if they use DHCP, what are the common ranges they are using? Because that's what you need to scan for automatically. Of course, but that would be another talk. Once you have found some addresses, there are lots of stuff you can do to find out the rest. But then again, as I said, I can only do 60–70% of the stuff here. Yeah.
Okay.
No more questions?
Yeah.
Thank you very much for attending.
Another question from the peace missions.
Okay.
So, do you think
guys.
the layer 2 vulnerabilities can be fixed without changing the layer 2 or doing stuff in the switches like dynamic ARP inspection?
Actually, that's something Cisco wants to press currently in the RFC and IETF committees. They want to have the SEND protocol, so Secure Encrypted Neighbor Discovery Protocol, blah, 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 that this is actually happening in the switches, which only makes kind of sense. But that's actually something you could do. Of course, there is a detection of most of the attacks I present here, that's possible. But preventing them, that's the hard part. Detecting is, for the most stuff, pretty easy, actually. Because, okay, there's a new router being announced, every system sees that and can say, okay, this is a new router, I never heard of that before. Let's send an alert or log message or something. Detecting is easy, but preventive controls, that's hard.
Okay, then there's someone who asked me to ask you about TCP crypt.
I have no clue what it is.
Okay.
But could be one of those many RFCs which you can't read because there's just too many and nobody's implementing them.
Okay, and the last question from the peace mission is, tell him another countermeasure is to have switches that are IPv6 aware and do not allow sending of those messages on client ports.
Well, that would mean that you can specify filter lists and say these ports are clients, so ACLs on layer 3. Of course you can do that if your switch supports that.
I have a question. Now, currently, if you set up everything addresses and DNS and routers fixed, this is not working. I mean, what I wanted to tell, if you, for example, IPv4 also, you can send a fake, if you set up a router and a client or server who is, let's say, connecting to DHCP, and you spoof another DHCP, you can make a man in the middle, now, currently, with IPv4. And this, with IPv6 is the same. And if you set up a fixed IP addresses and fixed DHCP, you cannot spoof, or with IPv4 or with IPv6.
Yes and no. I get your question.
Okay, I just want to say that this is not IPv6 problem, but it's a general problem.
It's a general problem because IPv6 is 15 years old, and the security in the protocol is 15 years old. So you have what you have in IPv4, you have in IPv6. If you configure everything static, still some of the attacks are possible because duplicated address detection is still done, even if it's hard configured addresses. The redirect attacks are still possible, and so on and so on. So there's still stuff you can do also. Of course, you're way safer if you do everything statically.
Okay, but it is an implementation problem, and it's not an IPv6 problem. IPv4 is also have the same problems. You can do the man in the middle, just send a DHCP and another parameters for me, and I route my traffic to the real router. It's the same.
Let me put it like that. How old is IPv4? How many years?
I don't know exactly.
25 years maybe? Longer? Okay. Something like that, I think.
But
they haven't learned in the 10 years where all the issues were already known. And that's the basic part of the problem. It's a design problem, protocol design problem.
And is there a solution?
As I said, send IPsec client configuration, but this will take some time. Currently, no. In the future, hopefully. But I will do some more talks about that once this is done. Because one new technology, more problems.
Thank you, thank you.
Are there any more questions? So let's just thank Mark and be done for the day.